Right. So today we're going deep on something pretty cool that's like really on the cutting edge
Yeah.
of how large language models are going to be able to handle just the crazy amounts of data that are out there.
Yeah.
It's all about making them like super efficient at
Yeah.
understanding really, really long pieces of text.
Yeah.
So think of this as kind of a sneak peek into like how the next generation of AI is going to be built to just eat up everything from,
Right.
giant reports to like those endless email threads we all have
Yeah, absolutely.
without, needing a supercomputer in your basement.
But that's the dream, isn't it? I mean,
Right.
for a while, the whole story with LLMs has been all about size.
Right.
Like how many parameters can you cram in there?
Right. More is better.
More is better. Exactly.
Right.
But when you start using these things for like summarizing a whole research paper
Hmm.
or having a proper back and forth conversation that actually remembers what you talked about,
Yeah.
that long context understanding becomes like the main event.
Absolutely. And that's where the challenge comes in, right? It's like, how
Yes.
do you make these models understand like epic lengths of text,
Yeah.
but without, breaking the bank on computing power and memory?
Right. It's like trying to follow a conversation with like 20 people all talking at once.
Mm-hmm.
Your brain just can't keep up.
Right. Like total brain overload.
Exactly. And for LLMs, that overload means slower speeds,
Yeah.
higher costs. Nobody wants that.
Good.
Not good at all.
So while everybody's like focused on bigger models, more training data,
Yeah.
we're going a different route
A
today.
little bit more under the hood?
Yeah, like more vital, I think.
Definitely.
It's all about how the length of the text that a model can handle,
Right.
and specifically the way its like attention system is organized,
Yes.
can make or break how efficiently it runs.
This is the key.
Yeah.
So for our deep dive today, we're looking at this paper,
Uh-huh.
Cost Optimal Grouped Query Attention for Long Context LLMs.
Catchy title.
Really rolls off the tongue. But it gets into this really cool technique called grouped query attention.
Okay, GQA.
GQA, that's the one.
Okay.
And it shows how just by changing the setup of like the internal bits,
Uh-huh.
specifically something called query and key value heads,
Okay.
you can get massive efficiency gains,
Mm-hmm.
especially when you're working with those super long texts.
Okay, so it's like a more efficient engine under the hood.
It is. It's all about architecture, baby.
So the paper starts off by pointing out that in like most of the top LLMs today,
Right.
there's this direct link between the size of those attention processing units,
Yeah, the heads.
the heads, yeah, and like the overall internal complexity of the model.
Yeah, what we call the hidden dimension.
Hidden dimension.
It's like saying every department in a company
yeah.
has to have the same budget and the same number of people,
Oh,
whether they're like the mailroom or the research and development team.
gotcha. So not super efficient.
Not really, no.
Okay, so what did these researchers do differently?
Well, they did something really interesting. They decided to treat the number of query heads.
Okay.
Think of those as the parts that are formulating the questions when they're looking at the text,
Uh-huh.
and the number of key value heads, which manage the information the model uses to answer those questions.
Okay.
They treated them as independent things you could tweak.
Okay.
They basically decoupled them. And that has some really big implications for how much computing power and memory you need.
The FLOPs and the memory?
Exactly.
Okay, so
Yeah.
why is this decoupling such a big deal?
Well, think about it. When an LLM is chewing on text, especially long stuff,
Yeah.
one of the biggest bottlenecks comes from keeping track of all the key and value vectors in the attention blocks.
Uh-huh.
This is what we call the KV cache. It's basically the model's short-term memory for what it's reading.
Okay, like it's working memory.
Exactly. And here's the kicker.
Yeah.
The size of that memory grows directly with how much text you feed in.
So the longer the document, the more memory it needs just to hold on to all that.
It's CAC. It's like trying to remember a shopping list with 1,000 items.
Right. Yeah, I can barely remember like 5 things.
And it's not just memory usage. There's a ton of calculations involved too.
Oh, right. Yeah, because it has to figure out how all those words relate to each other.
Exactly. The attention mechanism has to calculate how every word in the context relates to every other word.
And then put it all together somehow.
And then combine it all in a weighted way. So yeah, that gets expensive really fast with long sequences.
So it's like the memory and the computation both just go through the roof.
They do. And
Yeah.
the paper mentions that people have tried to tackle this with things like shrinking the KD cache
Okay.
or using attention mechanisms that don't look at every single word pair
Right.
but their focus is specifically on optimizing this GQA thing.
Okay, so let's talk about that.
Right.
Grouped query attention, or GQA.
GQA.
It's all about bringing down those costs, right?
Yes, it is.
Yeah.
So at its heart, GQA is a way to streamline the attention process by having groups of query heads share the same key and value information.
So it's like instead of every researcher having their own set of books,
Right.
they all share a library.
Exactly. It's much more efficient. Instead of every single query head having his own dedicated KV vectors,
Uh-huh.
you have fewer sets of these vectors that are shared across multiple query heads.
So less stuff to store and fewer calculations to do.
Precisely.
Okay, now the paper also mentioned that multi-head attention, or MHA, is like a specific type of GQA.
Yes, MHA is just a special case of GQA where every single query head has its own unique set of KV vectors.
So it's like GQA, but without the sharing.
Exactly.
Okay, so they're saying that the way GQA is usually implemented isn't as efficient as it could be.
Yeah, they found a couple of key limitations.
What are they?
So first, remember how we talked about how most models tie the total size of the attention heads to the overall hidden size?
Yeah, like every department has the same budget.
That's the one, well, that actually prevents GQA from really cutting down on the total amount of computation needed.
So it's like having a fuel-efficient engine, but in
Yeah.
a really heavy car.
Yeah, the car's weight is holding you back.
Okay, so that's one limitation. What's the other?
The second issue is that current models don't really consider how the length of the text they'll be processing
Yeah.
should affect how they set up those attention heads in the sharing groups.
Oh, so they're not optimizing based on whether they'll be reading tweets or encyclopedias.
Exactly. It's like using the same running shoes for a sprint and a marathon.
Okay, gotcha. And then they go into these cost formulas, which I have to admit
Yeah.
look a little scary.
They can be a bit intimidating.
But what's the basic idea behind them?
Well, they're basically trying to put numbers on three main types of costs.
Okay.
The computation needed when the model is making predictions.
The inference, FLOPs,
That's one, the memory needed during prediction.
inference memory,
Yep. And the computation needed to train the model in the first place.
training, FLOPs.
You got it.
Okay.
And the key distinction they make is between parametric costs, which are tied to the model's size and complexity, and non-parametric costs, which are the ones that really explode when you crank up the input text length.
Because of the attention mechanism.
Exactly. Things like calculating which words to focus on and the memory used by that KV cache.
So the non-parametric costs are all about context.
Context is king.
Okay, so what do those formulas tell us about how to make more efficient LLMs for long context?
Well, they highlight three big things. First,
Yeah.
they show that we have control over how our resources are used.
Okay.
We can adjust the overall size of a model,
Okay.
the number of query heads,
Uh-huh.
and the number of KV heads to manage those resources.
So it's like we've got these control knobs we can tweak.
Exactly.
What's the second takeaway?
The second is that there's no one perfect setting for those knobs.
Okay.
It all depends on how long the text you'll be feeding it is.
Because of those non-parametric costs?
Exactly. If you're planning on dealing with really long sequences, you'll need a different setup than if you're mostly handling short stuff.
So it's like horses for courses, right?
You got.
And the third big takeaway.
The third one is maybe the most exciting.
Mm-hmm.
It's that by balancing those fixed model costs,
To parametric ones.
yep, with the input-dependent ones,
So non-parametric.
you can actually design models that are not only more efficient,
Uh-huh.
but also perform better, specifically for the context lengths they're designed for.
So it's not just about saving money, it's about getting smarter models too.
It's a win-win.
All right, so how did they test all this out?
They ran a bunch of experiments.
Okay.
They started with a model architecture
Yeah.
similar to Llama 3,
One of the big ones.
one of the best.
Yeah.
And they played around with different model sizes, context lengths,
Uh-huh.
and of course those all-important head configurations.
Okay.
To keep things fair, they kept certain things consistent, like the ratio between the model's complexity and the number of layers
Okay.
and the size of each individual attention head.
They controlled for all those variables.
Exactly. They wanted to isolate the effects of the head configurations.
Right, and what did they find?
Okay, so the
That's
big
good.
shocker is that the GQA setup that's used in a lot of today's state-of-the-art models,
Okay.
where the number of query heads is based on the model size and the head size,
Uh-huh.
and they use like 8 kV heads like in the Llama 3.21b,
Yeah.
it turns out that's not great, especially for really long contexts, like 128,000 tokens.
So it's not as efficient as it could be.
Not even close.
Okay, so what happens when you tweak those settings?
Well, they found that by using a different configuration,
Uh-huh.
for example, way fewer query heads, maybe just 8,
Okay.
and even fewer KV heads, like just 1.
Whoa, really? Just one?
Yeah, and then bumping up the overall model size a bit.
Gr-
They could get the same level of performance,
Okay.
but with way less memory and computation.
So how much less are we talking about?
For that 128K context length,
Yeah.
they saw about a 48% drop in inference memory
Wow.
and almost a 50% reduction in FLOPs.
That's huge.
Those are massive efficiency gains.
Just by tweaking the heads.
Attention heads are where it's at.
So did they find any other interesting relationships between the query and KV heads?
They did. They looked really closely at the trade-offs.
Uh-huh.
They found that reducing KV heads really slashes memory usage
Okay.
without affecting computation too much.
Uh,
But reducing query heads hits computation harder.
okay.
But here's the really interesting bit for you.
Yeah.
Changing the number of query heads seems to have a bigger impact on how well the model actually understands language.
Really, that's kind of surprising. You'd think the keys and values would be more important for understanding.
You would. But their theory is that more query heads give the attention layers more expressive power.
Like more ways to look at the information.
Exactly. It's like having more perspectives on a problem.
So more KV heads just means more data.
Yeah, more raw material.
But more query heads means more ways to process it.
Exactly.
Fascinating.
And then there's the whole thing about scaling laws for attention heads.
Right. What's that all?
This is one of the cool new things in the paper.
Yeah.
They found that the relationship between how well the model performs,
the loss.
yep, and the number of attention heads follows a very predictable mathematical pattern.
Okay, so like a formula.
Exactly, a power plus constant function.
And that held true across different model sizes and context lengths?
It did across the board.
Wow, so what's the practical use of knowing that?
Well, it tells you that there's a point of diminishing returns when you just keep adding more attention heads. After a certain point, you're not getting as much bang for your buck.
So it's like you don't need to just keep throwing heads at the problem.
Exactly. You can be smarter about it.
And what about when they kept the KV heads constant but scaled up the model size and the query heads?
Ah, good question. In that case, they saw a different pattern.
Oh, yeah.
It became logarithmic instead of that power plus constant thing.
Interesting. So different scaling laws depending on how you tweak the heads.
Exactly. It's all about understanding those nuances.
Okay, now what about the length of the text the models were trained on? Does that affect these findings?
They found that as long as you train on sufficiently long contexts, the exact length doesn't really change the difference in performance between different numbers of query heads.
So those scaling laws still apply?
They seem to.
Okay, and what about if you start with a model trained on shorter text and then want to use it for longer stuff?
They actually tested that too.
Oh, cool.
They took a model trained on short sequences.
Yeah.
And then kept training it on much longer ones.
Uh-huh.
And guess what? It caught up to a model trained from scratch on long sequences really quickly.
So you don't necessarily need to train on super long stuff from the get-go.
Exactly. You can adapt a model trained on shorter text, which is often more efficient.
Okay, so to sum up, what's the main takeaway for our listener?
The big takeaway is that by fine-tuning those query and key value heads in GQA, we can make LLMs way more efficient at handling super long text without sacrificing their ability to understand and generate language.
So big savings on computing power and memory.
Huge saving.
And why should someone who's not like an AI expert care about this?
Because this is the future of LLMs. We're talking about making these powerful long context models way more accessible and affordable.
For all kinds of applications.
Exactly. Think about anything that needs to process tons of information like business intelligence, personal assistance. This is how we're going to make those things truly intelligent.
So it's not just about bigger models anymore, it's about smarter models.
It's about working smarter, not harder.
I like that.
So here's something for you to think about.
Okay.
How could these advancements in long context processing unlock entirely new AI applications?
Stuff we haven't even thought of yet.
Exactly.
That's pretty exciting.
It is. And if you're the kind of person who likes to get their hands dirty, the researchers actually made their code and data public.
Oh, cool.
So you can dive in and explore.
Awesome.
This is a really hot area of research with the potential to change the whole AI game.
This is The Deep Dive. Thanks for listening.
Thanks for having me.